All right, in this podcast, what we're talking about, we're kind of continuing the discussion in Chapter 7, and we're doing a little bit more of a sophisticated discussion about the use of multiple patterns to create functions. And we're actually going to see, I raised a question earlier about why would you want, why would you want a thing like F0 where if I don't get it, everything's dumb. We're going to kind of answer that question right here. So this is an example. There's a couple of things I want you to kind of note. The first one is that, so I declare this function f, right? And I require the parameter 0, the value 0, and then all this function is going to do is print the word 0. And then I have the vertical bar, right? The or sign, if you want to look at it that way, or the Unix pipe, whatever you want to call that thing, the vertical bar. It's the or sign. And what it basically says is, okay, I got a function, f defined this way, and I got the same function f also defined this way, right? And now note a couple things. It says match non-exhaustive again, right? And it basically tells me that I got 0 and I got 1. If you look at this for a second, what you realize is that it'll be fine on a 0 or a 1, and it'll be bad on everything else. There's sort of no default, like what if that's not there? So that's what the match non-exhaustive gets me. I can also see that f is defined as a function with a input value of integer and a exit value or a return value of string. Okay, I say f space 1, and it evaluates to the string, right? It equals the string 1, which is a string. So the concept right here is that I can actually, I can just declare multiple realities for the function, what its behavior is, what it is, and what it wants to receive. So if here's kind of the syntax, and I knew you were asking ever since chapters 2 and 3 that we skipped. I know that you were saying to yourself, yeah, but when are we going to see grammars written in BNF or some similar sort of grammar notation? Well, welcome to it. So here's the idea. Reading from the top, a function definition is defined as the : equal just kind of means is defined as the keyword fun followed by this thing called fun bodies. Fun, it's horrible. We should find other words. That's it. Okay, fun bodies is defined. I'm not actually sure if this is a typo, to be honest. I got fun body or fun body. Now the first or is actually within the grammar. Okay, the second or is in quotes, and that is an actual character that needs to be typed. All right. I believe that ought to be something like an empty version or a real version. Fun bodies is basically either nothing or fun body, and then if there's a fun body, then the vertical or followed by fun bodies, which again can be something or nothing, and then fun body is defined as a function name, and then a pattern equals, and then some expression, and that's the pattern. I don't know if that's helpful to you, but that's the syntax as we would define it. And this is the kind of stuff that you got to get deep into when you get to compilers. So in this case, let's look at an example that kind of answers the old question, which is I got this function f, and I say function f 0, and the real critical thing here is this is a little confusing if you look at this. You got the hyphen, right? That non-bolded hyphen. That's the command prompt. When I get to function f0 equals quote 0, and there's no semicolon, we're still going. The equal sign is a prompt. The first equal sign is a prompt from SML saying keep typing. Okay, so you kind of almost have to just mask off those, the hyphen and the equals on the far left of those first two rows. So I basically got the or sign there says I've got two ways of thinking of this function. I've got f with 0, in which case the whole thing the function does is just prints the word 0. And then I can say f underscore, remember underscore, matches anything. So essentially what I've done here, if you think about this, is I have created the if then else statement, right? Or really, this is really more of an if then, right? If I were to go f0, f1, f2, f3, f4, and then f underscore, I would create the if then, else if then, if else if then, else if then, else. I would be creating the nested if then else statement. I mean, that's really what we're doing here, right? If it's zero, do this. Otherwise, say non-zero. So that's an example of creating a certain kind of structure that we're comfortable with in imperative languages and object-oriented languages, which are really, as we've talked about, basically imperative languages with an object-oriented wrapper. Okay, so in this case, I say F0 and the value is 0. I say F34 and the value is non-zero. That's it. Okay, so case in point. In these, we have two examples, right? That these two definitions that do the exact same thing, two different function definitions. And I wish there was a little white space in between there, but I got a function f, right? In the first case, I use the multiple patterns approach. So when if somebody calls f with 0, I do that one. An alternate definition is an f with anything else, they get non-zero. Well, that's exactly the same as if we declared a function with some for some value n, a variable, and then just checked internally. If f is 0, then print 0, else kind of print non-zero. ML programmers prefer the pattern matching style. And if you think about it, it's actually a pretty kind of a cool thing. It does give you shorter, more legible functions, but I think one of the things that it does, when you deal with recursion struggles to in imperative languages, in part because it's nested in all this, if n is 0, then 0, else, especially when you get into calling recursive functions. But I'll give you an example. Let's go to the next one. Here's the factorial program that came out of chapter 5. Up top, we go, fun, factorial, n equals, right? And if n is 0, then it's 1. Otherwise, we take n times factorial times n minus 1. We make it, we call it, sorry, not factorial times, factorial calling n minus 1. And, that's kind of, it's recursion, but it's got that little bit of imperative feel. In the second one, you can see the base case just staring at you. It's like, it's almost like I'm saying, function, base case is 0. And in that case, the value is 1. If it's not the base case, then I'm going to define n to be n times the factorial of n minus 1. And it suddenly, conceptually just falls out really easily compared to trying to, it's like the cognitive structures are just laid out in front of you more. Here's another example from chapter 5 also. This was the reverse function. I take a list, okay? And I'm making a function called reverse. It's going to take a list as a parameter. In the first one, I have to say if null L, which is a test. Null is the function that tests to see if the list is empty. Returns a Boolean. If the list is empty, then evaluate to nil. Else, I call myself with the tail of L, and then I concatenate that to, I take the head of L, which is a single element, I put brackets around it to make it a list, and then I concatenate those two lists. And I'm flipping the orders, right? We did that. In this second example, now we're using patterns. So I say that function reverse, what's the base case? If I'm looking at a string and I'm chunking it one at a time, I chunk one off, I got the rest. Chunk it again, I got the rest. I keep chunking until I run out of list. And when I run out of list, that's because the value is nil. So the pattern says, if what you called me with was nil, then my evaluation is nil. And then I can also say, or you called me with some other string pattern with first, and then that's the cons operator again, first and the rest. And my definition in that case is going to be that I will call reverse with, I'll take rest, which is a list. I'm going to concatenate that to first, which has been turned into, it's an element, right? It's the first element of the list, and it's being turned into a list, and I'm going to concatenate it. It's not only fewer words, the word reverse occurs 3 times, right? And then if you look outside that, you take away the keyword fun, you take away reverse, which is the name of it, which occurs 3 times. When I'm defining it once, I'm defining it again, and then I'm calling it. When you take those away, there's literally only 6 kind of words left. And it just begins to be conceptually much simpler. Okay, let's do some other examples because this is going to evoke some of the subtlety. Okay. So this example is when we're going to take the elements of a list and we are going to just add them all up. So it's going to take as its input, a list, and then as its output, it's going to yield a number, an integer, because it's going to take each element of that list is going to be a list of integers. And I haven't run it or looked at it, but it just seems like that's what it's got to be, right? And so again, we see that same idea. The one thing we see here as a bit of a variant that we didn't fully see, in the previous examples, is after the first part. Well, first of all, let's break up the first part. I got a function f, right? If I've got nil coming in, then the answer is 0, right? I'm adding the elements of a list. I look at the element. If there's nothing left, right? Remember again, how we do recursion. You give me a list. I take the first one. I add it to whatever I got. I hang on to it. And then I take the rest of the list. I add it to the rest of the list. And so what I do inside here is I say first and rest. I use that pattern again with the cons operator. And if it's nil, I'm 0. And if it's not, I get to this next part where it's always going to be first and rest anytime it's a list. And I'm going to be first plus, and then I call the function f with rest. So that's the new list, right? And all these are going to evaluate their way back up. What I've got in the second example is instead of 2 options, multiple patterns, I've got a base case and sort of the rest. In this case, I've got a base case and 2 alternatives, right? 2 additional ways of dealing with this thing. And so I still got, so this is an example of counting the true values, right, in a list. So in this one, I've still got this notion of nil, my base case, when I run out a list. In the meantime, I've got this pattern, which is true appended to the rest and false appended to the rest, okay? And so in the case of true, where true is the first, so in other words, I'm creating a pattern where there's a list, and I've got rest, which is also a list, and I've got true, which is a Boolean value. So if the first one's true, and then I'm going to do this first one, and if the first one's false, I'll do the second one. If it's true, I'm going to add 1. I'm going to say 1 plus, call the function for the rest of the list. If it's false, I just call the rest of the list. In other words, I'm just moving on. So I hope that kind of makes sense, what we're doing there. And in a Boolean list, if I look at each element of the list, it's going to be true or false. I've exhausted all the possibilities there. So this is going to cover all the cases, and I'm not going to get that goofy warning about match non-exhaustive. Here's another one that's kind of interesting, a little funky, which is making a list of integers where everyone is bigger than the one in the original list. So if I pass it, 1, 2, 3, 4, 5, and it would create the list 2, 3, 4, 5, 6. That'd be the idea. Same thing. If I run out of a list, the answer is nil. If I've still got some list, I take the first as the first element, essentially the head. I take the rest, which is the rest of the list. Could be null, but it's the rest of the list. And then I take first plus 1, and I concatenate it to calling f with the rest of the list. Okay? And you might want to ask yourself, why don't I just concatenate it to the rest of the list? Well, because the rest of the list hasn't been modified yet, but f, the rest of the list, f rest, is the modified version of that. So there's some conceptual things to kind of get our heads around here, which I'll do in class to kind of help reinforce some of these ideas. But I think you sort of, again, see some of the power in this. One restriction that just to keep in mind, you might think to yourself, well, using patterns, why don't I do something like function f, this one that under this is not legal, function f AA, which would be a pattern in which the 2 values are equal. And I would say, good on you if that was your idea, but it turns out that in ML you can't do that. I don't know all the reasons why. We still are stuck with taking an A and a B and then comparing them, okay? So I apologize for that. Not my fault. And I don't know what the particular logistical dynamics were that led them to not permitting that pattern, because I think it's a fairly cool concept, but we can't do it, okay, in ML. And finally, this is the last slide of this section where we're talking about patterns in this podcast. It's really just kind of reinforcing the concept that I can establish patterns. I use them all over the place in ML and in functional languages. So I can declare a value, which is a tuple with, A and B, and then I'm giving them an integer and a real, right? And then I'm going to say val A is 1, val B is 2.3. Really, it's really just a pattern, and I'm matching it. When I say val A colon B, give me that const again, right? Then I see that what comes on the other side is a list, and remember that A colon B is a pattern that says A is the first one, right? Because that's the const operator, which wants to have an element and then the rest of that list. That's how const works. We do get the warning, binding not exhaustive, right? Binding not exhaustive, which is dealing. What do we have before? Match non-exhaustive was our previous one. Now we're going to say binding non-exhaustive, and A is going to be 1, and B is going to be the element 1, and B is going to be the list of integers. So just to kind of recognize that patterns are not just for function definition, and we'll see much more as we get into I don't know which chapter, 9 maybe. We're going to get into other patterns in ML, and but for now, this is at least kind of an introduction to the concept, and I hope you can see how powerful that is, how much easier programming becomes, but especially in the sense that instead of you having to tell me how to do it, it's really a lot more declarative. I'm just going to say, it looks like this, and you're like, oh, okay. Like, I'm going to give you a stack of money, and the pattern looks like this, and you go, oh, I now know what to do with the money, because it's declarative really in that sense, that the programmer doesn't have to know everything to do in order to make that happen.